Hi, everyone. Welcome to our session. My name is Weigang. Here with me, my colleague, Debashis. We are both software architects from the CX Customer Delivery team. We are currently working on DISH SDN controller delivery. I am leading CNC Crosswork Network Controller delivery. In this session, I will cover details on CNC use cases. Debashis is leading the vRouter and the on-prem router lifecycle automation. He will cover from network lifecycle automation workflow use cases. The agenda of this session will cover SDNC. Actually, SDNC stands for SDN Controller Architecture. We'll go to a high level of automation solution overview, and then we'll deep dive several use cases. And the use case will cover closed loop use case, vRouter OS upgrade, ZTX, which includes ZTP and ZTO, and overlay configuration management. So to start, this is the architecture. If you look at the architecture, and from this slide, you can see SDN controller actually focusing on DISH network. It has two domains, transport domain and data center domain. The majority of SDN controllers focusing is getting insight of transport domain and provide automation of transport domain. Data center domain will provide the network insight, observability of data center domain, but the automation is out of scope. So today's session, our main focus will be lifecycle automation workflows and the network management. So from lifecycle, and this architecture, you can see it is divided into 4 groups. Lifecycle automation workflow covers zero-touch provisioning, zero-touch onboarding, and in addition to that, it also takes care of the network devices lifecycle automation, including config audit and the configure backup workflow with image upgrade testing. It goes through test automation, and also it has a backup and restore of the workflows. Once the device is ZTP'd, which means it has necessary day 0, day 1 configuration ready, it will take ZTO process to onboard it to CNC, which is this part. Okay, so this is the functionality of lifecycle automation takes care. It takes data from external system and also bootstrap the network. The network management is, in fact, a Crosswork Network Controller. It has components of NSO, CDG, PCE, which is not in the diagram, and also with the whole infrastructure. It has application of change automation, optimization engine, and the CCAP, which does the topology manager. So once the devices is onboarded on CNC, CNC starts collecting telemetry data from network devices through GNMI, and in addition, also collects SNMP and syslog information from the network. And those will be made available through the bottom Kafka message bus. So Kafka message bus here plays an integration point and makes data available, and also integrated performance management, which is a matrix of CX solution, and the Viatra for the fault management, and it consumes data. So that is the integration point. So in addition to that, you can also see we are actually also getting data from data center domain and make the statistics available through the dashboard of fault management and the performance management. on top, there is a unified portal, and the users or NOC team from customer can just access the unified portal, and then from unified portal, you'll be able to see the different UI from all the components. So this solution takes stage to be today's deployment. We started with verifying the functionality and the scale, and also the performance. We started doing this from the on-prem environment. So all the solutions being verified when the workload is on the on-prem, and convince customer that this works, meets their expectation. And then the next step, since this requirement, is having all the workflow 100% on AWS cloud. So currently, all the workflows for all those four groups are already 100% on AWS, which is a cloud environment. And it is currently managing a hybrid network, meaning those devices has two parts. There are on-prem devices, we usually call them CSRs, and it also has a cloud-based devices, we call them like vRouters. So that's how we are here today. And our goal is currently some of the workloads, for example, CNC is still EC2 based, not 100% cloud native per se, but the goal of by next year, all the workflow will be cloud native and deployed as an EKS. Okay, so that's the architecture, and I'm going to go over a little bit detail of the use cases. And this part is for CNC use cases. So we provide a topology view of the network as the topology manager. And then CDG plays as a data collector. Our network size is about like our goal is to have 35K devices to be managed. So we actually deployed about 72 CDGs in 3 different regions and in different available zones. So those are the data collector. And the data, once data is collected, and oh, by the way, the data is collected, I think I probably mentioned in the previous slide, it includes telemetry, so GNMI, and also syslogs and SNMP tracks. Those data distributed to Kafka, and the matrix VHRA consumes data to do anomaly analysis and AI ops analysis, and made the data available through dashboard. And we have COE for path optimization, NSO for SR-PCE, L3, L2, L3 VPN, and also our use case is to provide 5G slicing for transport. And that work is in progress. This is the third functionality we provide, and we recently add change automation to CNC. Change automation is being used. Number one is for device configuration changes, management, and some of the we have used NSO for service provisioning, but in addition, if there's some configuration change required, we use change automation, and that change automation is doing the configuration management with pre and post checks. And we also use change automation as part of device move and image management. And also we do it, we go through a couple of use cases for network remediation. So that is the network management use cases. One more group of use cases I wanted to touch upon is it's the closed loop remediation. our requirement from Dish is we have to have a self-healing network. We nowadays cannot afford anything happen in the network needs human intervention. So this is what we do, and this closed loop is combining SDNC's observability with automation. So from the architecture, we can see we have network management, and we have performance management and fault management through Virtual and Matrix. And then we combine this. When we detect some anomaly, we can trigger an action automatically. So in high level, what we do for closed loop is we use CDG again as telemetry data collection, and then we use Kafka as a messaging bus, and Matrix Virtual is doing the anomaly detection and AI ops to decide in what case we should trigger a remediation. And then once it triggers, the action is actually performed through CNC's CA change automation or NSO. That's where each component plays. We currently have more than 14 closed loop use cases defined, and there's one top on the list of the use case is doing the memory leak, and then detecting memory leak triggers process restart. This one is the number one use cases Dish wants to implement, so it is currently in implementation. We had a couple incidents happened before the solution put in there, and it took humans to go in there and check the process and detect the memory leak, and then have to manually restart. It's very time-consuming and lose a lot of observability of the device, and also lose traffic. So a little bit detail of this sample memory leak, how we do it, and this is a very high level. It's a sequence diagram to show the whole process. And we have one party is network devices, and it's there, and the CDG has already created collection jobs, continuously collect process status data, and meanwhile published data through Kafka, and Matrix subscribe this data through a special topic and continue monitoring it. When it detects anomaly, it actually sends an alert to Virtual, and the Virtual will do some AI ops and decide what is this just temporary, or should we trigger remediation? That's the decision is made by Virtual. Once the trigger decision is made, it invokes CNC and SO automatically to restart a setup process. And once this is restarted, network devices should become normal. And then going through the same data published process, Matrix will find the process network consumption, memory consumption is back to normal, and they'll clean the anomaly. That is a way to close the whole loop. So this is one example of a closed loop. We have 14 more to be implemented, and I'm not going to go through that. So from this point, I'll hand off to Debashis to cover use cases of router lifecycle management. Debashis.
Hi, I'm Debashis Kundu. I'm leading the Dish, day two automations, lifecycle management efforts, and I'm going to cover some of the use cases that we are doing as part of device lifecycle management, specifically orchestrating and process automation perspective, some of the use cases that I'm going to deep dive into a little bit details. So here's the high-level use cases that we are doing as of today. We are doing zero-touch provisioning with orchestration, including device onboarding to the SDN controller, activating the device, making sure that all the test cases pre-check, post-check, along with any other test cases that we are executing as part of the GTF, also get executed as part of the overall onboarding process perspective. Then we are also doing compliance audit. So as you know, like compliance is a big issue for network management perspective. So we have a pretty GCT-based compliance audit, golden config-based compliance audit, which are pretty much written in NSO packages. And also we have a config-led based compliance audit and remediation, which is a little bit smaller chunk of the configuration that you can surgically update or audit and then remediate in terms of your config management perspective. Config backup is one of the issue that we tackle initially. So right now, all the 35,000 devices, or what the total number of devices, including vOrders and the on-prem devices, are getting backed up to the Git lab inside Dish. So we are backing regularly in terms of all the vOrders and the on-prem devices. And then in case there is an issue and we can automatically restore the config also. So versioning controls is the main kind of pain point that we wanted to solve here, so that we have older version in the GitLab to kind of go back in case we run into some issues in the newer version of the config template and things like that. So we can quickly back up and we can quickly restore the config in case of there is an issue. And I'll cover a little bit deep dive into device OS upgrade along with smooth upgrade, how we are doing. In specifically, I'll cover the vOrders portion today. And on-prem device upgrade is pretty standard in mode upgrade. So it's kind of inclusive of vOrders. So vOrders has both in mode and auto mode upgrade process built into the OS upgrade. And then the device config lifecycle management perspective, we try to stick with as much as possible with golden config or compliance audit and remediation in terms of any config changes that we are pushing to the network. We wanted to capture as part of the template updates, whether it's the config template updates or day one template update or config-led update, and kind of capture that and do an audit and push. But there are some exceptions where we have to change on-demand mask scale config changes. So we are also doing as part of overall lifecycle management in case there is a quick configuration change that we have to make without updating the golden config template or outside the golden config template process for a number of reasons, like, for example, the workaround and things like that. That also we are putting as part of the whole lifecycle management process perspective. So that's kind of high level, all the use cases we are doing today in terms of transport automation. So I'll go into deep dive into a few of these use cases and then kind of call flow wise how we are doing it and how different components are interacting each other, so that you get a view of the all the components, how it's working together. Okay, so here we are, this is kind of the high level of how the order onboarding call flow works. So we have AWS notification, the workflow gets triggered, BPA workflow gets triggered with a notification base. So this is essentially in the backend, there is the Lambda functions that basically monitor all the events from the vOrders as the vOrder is getting instantiated. They send events to the Lambda function, even to the CloudTrail forwards that event to the VPC of where our SDN controller is running using a Lambda functions and event bus. And then that Lambda function monitors the EC2 underlay interfaces as they are bringing up, and they can ping. Then once they are successfully launching a vOrder instance, then using the CloudFormation templates, then it sends a notification to us where we kickstart the workflow for vOrder onboarding call flow. So here, at the initially we tried to, because the device configurations that initially pushed is through the CloudFormation, so which will have pretty standard day zero config, and so we have to kind of onboard the device using the day zero auth group, which is a static auth group we define as part of the CloudFormation template, and then we add all of that vOrders or any devices that we are onboarding to the device group. These device groups get created based on the regions or market. So it's automatically based on host name. It kind of creates the device group automatically. And then we also fetch keys. We do a sync from and then we try to update the ICE so that we can actually we can kind of orchestrate the device through the ICE instead of going through a static off group. So this is where we kind of make sure that ICE is configured for the new device. So ICE, we push the ICE, and then we also push the day one config, right, using the day zero off group that we initially onboarded. So this is the golden configuration template based on the device roles and the flavors that we need to push. So there are multiple flavors of devices that we are supporting in VR side. And then it gets pushed based on that device roles or host name that comes with. It kind of identifies what type of day one config we need to push it out. Then as part of this day one config, it needs loopback 0, loopback 10, which we are going to allocate or going to get it from the info block. So it does query to the info block subnet based on the region, and then get that particular IP address for loopback 0, loopback 10 from the container. And then also it allocates the prefix seeds for that vRDS. And finally, it's going to push the day one config to the NSO, right? So day one config gets pushed out. Obviously, day one config has the ICE integration, so we have to change the output next, because otherwise the device will not be able to connect it. So we change the output to the day two output right here after pushing the day one config. So whatever we onboarded through initially, that output will change. Then we check the connectivity, making sure that we can access the device, and then we try to onboard the device. We trigger the onboarding process for SDN controller, which is like CNC here. So the device gets monitored automatically to the CNC, so that CNC can collect the telemetry, syslogs, and all the other information that is needed for overall network management perspective, right? And also, this is optionally, depending on the scenario, we also trigger a workflow for trigger to a CX staff, which is our test automation framework, to run certain number of test cases that validates the functionality of the day one configurations. So that's in a high level of the vRDS onboarding workflow. It has a lot of other stuff. I'm just trying to kind of showing high level what it does. As you can see, it interacts with NSO and then all the other components that we have here as part of the SDN controller, right? And so essentially it's pushing the configuration along with orchestrating the whole flow so that it can be monitored, from a performance fault and network management perspective, right? All right, so let me move to the next use case, which is vRDS OS upgrade call flow. So this is specifically cover current process that we are using for OS upgrade. Because these are virtual routers, and the way it works is the OS upgrade process is we kill the existing EC2 instance, and then we create a new instance with the same kind of flavors, right? The same configurations, and using the CloudFormation template. And then we have to using a new AMI image, right? So AMI is basically what we kind of upgrade to the new image. And then in case we need to push some SMU which are not part of the AMI, then we have a process to push those SMU also, which is kind of an in-mode upgrade, typically just like on-prem devices, right? So the first step is kind of we do a mass upgrade. So essentially we wanted to do a hundreds of devices upgrade per night. Currently we did last night around 60 devices upgrade. So the upgrades is kind of done through VPC. So each VPC in AWS, we have kind of 40, 50, 60 number of devices, vRDS under each VPC. So users select a VPC, and then we kind of select the devices underneath that VPC, whatever the devices is, it automatically knows that because those devices should be already onboarded, right? Then it either review the devices, and then it will config push to match. There are some workaround that we have to push it here to change the configurations, because the devices that get created newly using the new CloudFormation template versus the devices that is existing one, those are use two different config template or CloudFormation templates. So configuration wise, we run into issue when we restore the config with the a new CloudFormation template, it fails due to some of the admin level commands that get created in the new template. So just to kind of align with that, we do a kind of cleanup steps to match the config before and after, so that restoration process, there is no issue. So this is the steps where we config push to match the CloudFormation day 0 templates, and then we execute the pre-checks, which is basically a list of commands. And all these steps are done across all the devices in the device group, right, in this VPC. And then we isolate the device. This is basically we kind of shut down the interfaces that are not underlaid or any CNF interfaces that providing the services to the other components. So we kind of shut down so that we can isolate these devices for upgrade. We perform a backup of the device config, and then this is where actually once we've done all the prerequisite steps, we kind of trigger a process in the AWS, which is basically a EC2 replacement script. It invokes a EC2 replacement script. And this is where basically you kill the existing instance, you extract all the information from the existing instance, all the parameters, and then you create a new instance. And in these steps also, if there is a requirement to kind of update any static tables of the EC2 entries for the static entries, then it will also do that. So this script takes care of all the things. So we kind of invoke it. That script long term, we are trying to do a Lambda function here to kind of integrate with this. Right now it's a script based. We just invoke the script. Then we do the ping test, because now this process takes around 40-45 minutes. So after that, we kind of continuously run a ping test to check that the devices are ready for our pushing the day one config. So we just ping the underlay interface, and because they are going to get the same IP and same thing as the previous instance. So once the ping test successfully done for all the devices within the VPC, then it will move to the next step, which is basically again, same step, like we need to get onboard the device using a day 0 auth group, or essentially we need to use day 0 auth group to talk to the device, because at this point there is no config on the device. So we start kind of similar process like onboarding process, fetch the host keys, perform the config restore process. So essentially the configuration that we backed up, restore the config here. We change the day 1 auth group so that we can now, because as soon as we config restore, it will change to ICE. It will talk to the TACX servers and ICE. And that's where we need to change the auth group. We change the auth group, then we perform, depending on the requirements, if there is a need for smooth upgrade, we kind of invoke the CNC playbook. Right here, we invoke the CNC playbook to trigger the smooth upgrade playbook, right? And once that is done, then we kind of, there's a process here that we need to stop and start just to get cleaner update here. So we do a stop and start of the EC2 instance for the current EC2 instance, just to get a cleaner up in the smooth upgrade. Once we do that, this steps takes around 10 minutes. So once we do that, then we do again ping test to make sure that everything works fine. Then in this case, we are doing some additional steps for this upgrade where we are enabling the license server registration process. So in case we need to do some configuration update, those are the things that we picked up here. In this case, we are picking up the license configuration updates, and then we remove the isolation of the device. We execute the post check. We look into the post check diff, and that's pretty much then the device get onboarded, right? I mean, ready to go. Again, I'm skipping a lot of other details in the step, but this is high level sequence that we do as part of upgrade, and we are doing this for across like 60 to 100 devices per night, and it's been running pretty good. So whole process takes manually. If you do one device, it takes 3 hours, 3 to 4 hours. If you try to do, because this process takes 45 minutes, this process takes 10 minutes, this process takes 30 minutes. So if you calculate whole process, it's like 3 hours, and we are doing 100 devices. So that saves a lot of time. Just this use case itself, we are saving a lot of man hours in terms of efficiency and productivity perspective for Dish. Going to the next use case, this is kind of extension of that. It's showing that playbook, how we are doing the playbook. This is kind of the playbook for smooth upgrade, which is kind of a more of a smooth upgrade, as you can see. we check some of the package consistency, then we perform node lock on the device so that no configuration can be changed on the device. Then we install activate the package, install commit, and then we verify the package is committed list. And then that's where we stop and start. After this step is completed, then we stop and start to the EC2 instance to make sure that it's come up perfectly clean, right? Next, we'll move to the next slide. So this is a overlay configuration automation. So steps kind of showing the high level workflow, how we are doing it. So overlay, the way we are pushing, in AWS is we are building a overlay config, right? We are building a tunnel. All the BRs are talking inside the tunnel. We have all the routing protocols that are running, BGP, ISIS, and everything. So this framework is basically the bringing up the whole overlay config tunnels across all the BRs. So we create what we call an intra-VPC tunnel or inter-VPC tunnel between the two BRs. If the BRs consist of in the same region, same VPC, local VPC, then we create a intra-VPC tunnels between them. And if they are in a separate VPC, then we create a inter-VPC tunnels. And so one VRs, if you bring up a new VRs in a VPC, then it has to create all the tunnels within that local VPC. And let's say that local VPC, you have 20 VRs already. So it will create like 20 tunnels. Plus you have to create all the other, tunnels for the inter VPC tunnel. So you can imagine like one VPC. If you want to bring a new VRs, you have to create literally hundreds of tunnels. And that's where it's manually doing it is impossible to bring up automatically. Manually configuring hundreds of tunnels and stuff, right? So this use case is meant to be like configuration of the overlay config portion so that we can create hundreds of tunnels within a button, right? And this is in production days right now. Just high level, like basically user selects a VPC where they need to onboard the device or new device. And this mapping of VPCs, like which VPC talks to which VPC in terms of layer perspective, there are three hierarchical layers. One is we call it BDC, and then RDC and NDC. So each layer has different connectivity between the upper layers. So it can talk to up to two VPC in the upper layer, right? So based on that connectivity details, so we collect that in the initially or either define it how the VPCs are connected, and then based on that, it kind of automatically knows how many tunnels we have to create. So it finds all the devices of the local and the remote VPC, then it creates, it basically creates the mapping of that how many tunnels we have to create, and then we call the tunnel service, which is a sub workflows within the BPA, and essentially it invokes NSO actions for creating tunnels, and then user can review the dry runs of the tunnel config and push the commit to push all the tunnels across all the intra and inter VPC tunnels. This is kind of a high-level flow of that tunnel creation, only showing so as you start onboarding process, we trigger this process automatically through the onboarding process tunnel creation. So NSO gets the tunnel actions, and then NSO does the IP pull from the info block. So each tunnel has a separate, depending on which region it belongs to, we have a separate container for IP allocation. So we get that, we update those host entries using the extended attributes. We get the tunnel IDs from the resource pool, and then we push the config. And this flow is kind of repeats for all across hundreds of tunnels that we need to create. So this is just a snippet how in the backend works through NSO info blocks, and then if we optionally need to test something, we can also invoke the extra. So that's in a high level all the use cases that I wanted to cover today. And then I think there are many more use cases. Is there because of the time limit? I want to cover all the details. So hopefully that covers most of the high level use cases that we are doing in addition.